Well, hello everybody. Bev Try Thinking says all horizontals are parallel to the plane of the horizon, and he also says level is horizontal, but he has yet to provide any proof of any of that. I say, on the other hand, that all horizontals are not parallel to the plane of the horizon, and I say that level is definitely not horizontal, and I can prove it. That's what we're about to do. Now, Bev Try Thinking's logic is this. He says, if all horizontals are parallel to the plane of the horizon, P, then all horizontals are parallel to each other, Q. All horizontals are parallel to the plane of the horizon, therefore all horizontals are parallel to each other, both valid and sound, observable and verifiable. Well, I don't think so. That's a begging the question fallacy, Bev. The premises assume the conclusion to be true. You are assuming that there is one and only one plane of the horizon, ignoring any other possibility. Now, this is Bev's contention. If there were one and only one plane of the horizon, Bev might be right. But what he's asking you to believe is that a horizontal line parallel with the plane of the horizon in Miami, Florida, also has to be parallel to the plane of the horizon in Jacksonville, Florida, or in Boston. This is pure speculation. No testing or proof whatsoever, just a simple statement. The other possibility is if the Earth is an oblate sphere, then multiple planes of the horizon have to exist. Gravity vectors, that's verticals or zeniths, can't be parallel, and horizontals, which are perpendicular to those verticals, also cannot be parallel. So can we test this? Well, absolutely. We need two things. We need two fixed points, like a point there and a point there. And we need a way to measure angles A and B. And we'd like to do that simultaneously if possible. So how does that help us? Well, let's go to Euclid and Euclid's Elements, Book 1, Proposition 29, which says, a straight line falling on parallel straight lines makes the alternate angles equal to one another, the exterior angle equal to the interior and opposite angle, and the sum of the interior angles on the same side equal to two right angles. And further down we see Euclid say this, therefore the sum of the angles BGH, that's that one, and GHD, that's that one, also equals two right angles. BGH plus GHD equals 180 degrees. But what happens if lines AB and CD are not parallel with each other? What happens if they look like that? What happens if they are converging? Well, in that case, BGH and GHD have to be less than 180 degrees. That's easily provable. On the other hand, what happens if they look like that? What happens if they are diverging? Well, in that case, BGH and GHD have to be greater than 180 degrees. So the measurement process, we can test this with two theodolites. Those are instruments that precisely measure vertical and horizontal angles. We can put a theodolite at each of two positions and measure the vertical angle to the other theodolite. We'll put a theodolite there and we'll put another one over there. We'll point those two theodolites at each other and we will measure angles A and B. Now there's our little sketch from Euclid. Let's turn him so it looks a little more like our verticals here. And you can see that if the verticals are parallel, angle A plus angle B has to be equal to 180 degrees. It has no choice. They don't even have to be at the same elevation. The theodolites could be at two different elevations. You just need to be able to point the two theodolites at each other. So if Bev is right and all horizontals are parallel to the plane of the horizon, meaning all horizontals are parallel to each other, then all verticals must also be parallel, and the sum of internal angles, in other words, reciprocal zenith angles, has to be exactly 180 degrees, as Euclid Book 1, Proposition 29 says. But what if horizontals are tangents to a spherical surface? Then horizontals can never be parallel, nor can verticals be parallel. The sum of the internal angles, A and B, will be greater than 180 degrees in every case, if the surface of still water or points of constant elevation form a curve. By golly, we got us the makings of a test. Bev, let me introduce you to a couple of guys. One guy named Jesse Kozlowski and another guy named Larry Scott. In 2018, those two guys got together at the Hagerstown, Maryland airport and High Rock Lookout, about 11 miles apart, and measured reciprocal zenith angles. How about that? Larry was at the airport over there. That's Larry's theodolite and the signal mirror. And Jesse was up on top of High Rock Lookout. You can see where Jesse was located, where that red arrow is. Those two guys measured the two zenith angles. We'll call the one at the airport A and the one up on High Rock Lookout B. And here are the actual measurements. Larry measured angle A to be 88 degrees 57 minutes 58.2 seconds. Jesse measured angle B to be 91 degrees 9 minutes 55 seconds. That is a total of 180 degrees 7 minutes and 53.2 seconds. 180 degrees 7 minutes and 53.2 seconds. That is with no refraction correction. If you include refraction, that increases from 7 minutes 53.2 seconds to about 9 minutes and 40 seconds. Here's Larry's diagram with a little more detail on it. Again, there are the two angles that those guys measured, and there is the sum of those two angles. 180 degrees, 7 minutes, 53.2 seconds. That's 7 minutes, 53.2 seconds in excess of 180 degrees. Now, just in case you thought this was a one-off, this is a report done by NOAA back in 1978. It's a survey of the McDonald Observatory radial line scheme. They were measuring reciprocal zenith angles from 7 different positions to a place called Baldy. Here are those measurements. In the interest of time, I'm not going to go through all of this data, but I will call your attention to a couple of columns here. That one and that one. The first one is the sum of the zenith angles. The second column is plumb line tilt. That is simply the sum of the zenith angles minus 180 degrees. Notice that every one of them exceeds 180 degrees. The smallest is 15 minutes 53 seconds, and the largest is 44 minutes 33 seconds. So, now for the unavoidable truth. The zeniths are always doing this. So the horizontals are always doing that. Now for the conclusions. The sum of reciprocal zenith angle measurements always exceeds 180 degrees, therefore verticals are measurably not parallel. Horizontals, therefore, can never be parallel. And Bev's assumption that all horizontals are parallel has been shown to be false. Well, there's conclusive proof that horizontals are not parallel, all done and dusted. So let's move on to the fact that level is not horizontal, and we can prove that too. Let's talk about flagpole measurements. We probably all did this as a kid. You go out to the playground to the flagpole, measure a distance away from it that you know. You stand there with a protractor and a string with a weight on the end of it. Get your buddy to read the angle as you line the protractor up with the top of the flagpole. And if you know how high the protractor is at that point, just a little simple math and voila, you get the height of the flagpole. They do that in reality too. Surveyors do this all the time. At times all they're doing is trying to figure out how high a power line is over a road or something like that. But you can do it for other reasons too. And the interesting thing about it is this. If your baseline is mean sea level, for instance, It doesn't make any difference where you put that theodolite if that were truly a flat baseline. You can move the theodolite anywhere you want, and you'll still be able to calculate the correct height of a distant object like a radio tower. But because horizontal changes as we move over a curved surface, the trigonometric height, in other words, the calculated height of the tower above mean sea level, appears to change. The further away you go, the more it will drop. The closer you get to the tower, the higher it will be. And it's simply because that's what level is. When we reorient the theodolite like that, now we have a different horizontal. That's horizontal at the tower. This is horizontal at the instrument. So effectively, this is what happens. The tower now only looks like it's that tall. Well, in reality, we've got a real tower here. This is one from Larry Scott. This is not far from High Rock Lookout, about a mile or so away. There's a big red and white tower up there with a strobe on it. And Larry can see that thing from all over the county. Over a span of a few years, Larry has made measurements of that tower from a lot of different positions, 23 actually. Whenever he found a place where he could see the tower, he would stop when he had time, get out his theodolite, and take some readings. That's a plot of all the positions Larry measured from. I've shown the longest one there. You see the tower in the lower right. He got one measurement from 27.7 miles away. And here's all the data. The top number is the elevation of the tower that Larry was able to calculate, not the FAA elevation. This is Larry's calculation based on all of his measurements. And it's within a few feet of what the FAA says. But there's something interesting here. Notice the very first measurement was from 27 miles, and his instrument elevation was 1961. He's about 390 feet lower than the tower. Oddly enough, he's having to look down to see it. You see in the right-hand column all of the tower height calculations that Larry made, and they're all over the place. That's because that is the calculated height of the tower without considering Earth curvature. When you plot that data, it looks like that. You see that pretty curve. It's almost a perfect fit. R squared on that data is 0.9999. I decided to take a look at a couple of points, that point and that point. Well, you can see that at the distant target of 27 miles, the predicted drop's 431.3 feet. The measured drop is 434 feet. That's 2.7 feet difference. It seems to be fitting 8 inches per mile squared pretty well with refraction. Same thing on that center point. 145.7 is the predicted drop based on my calculation. 144 feet is what Larry got. That's 1.7 feet different. Larry went ahead and took all that data and applied both curvature correction as well as refraction correction, and you end up with a straight line, nearly perfectly straight. Notice that vertical scale. Those blue dots are not more than 3 feet apart. So that's Earth curvature you're seeing. That is level deviating from horizontal. But we can do that with just observations too. An autolevel is a great device. We set an autolevel up. It establishes vertical by referencing itself to gravity, and it makes a horizontal plane of reference for you, which is 90 degrees to the vertical. That horizontal will extend all the way to infinity, but in reality, you're going to become limited by what you can see through the atmosphere. Now, if the reference surface were flat as that's being shown, that horizontal will always be the same distance above the reference surface, always. If it's 5 feet at the theodolite, 30 miles away, it will still be 5 feet above that flat surface. The problem is, that's not what the Earth looks like. The Earth looks like that. And the gravity vector is different, and horizontal is different, as we've already seen. So let's move on to an observation that Bev really hates, and it's Blackpool Tower. Bev's auto level is set up, and the crosshair is just a few feet above sea level, probably less than 10. Google Earth says that beach he's standing on is at sea level. But look 13 miles away at Blackpool Tower in the distance, and the crosshair is 100 feet up on that building. I'm going to fade in a picture of the actual building. There's the crosshair. There's a red reference line. Now watch the building. I'll fade it back out. Keep your eye on it. And the match is almost perfect. Same thing we see in Bev's photograph. That's where the crosshair is striking that building. And that is about 95 feet above sea level. So that's reality. We have an auto level that's establishing a horizontal plane of reference. We got Bev in the foreground, just 400 or 500 yards away. But we got Blackpool in the distance, 13 miles away, and that 5-foot high auto level above that beach surface should be striking Blackpool Tower 5 feet above sea level, if level is horizontal. Problem is, level is not horizontal. The auto level crosshair is on Blackpool Tower at about that point. That's because that's what the Earth looks like. That's horizontal, that's level, and they're not the same. Predicted drop is about 95 feet, and that's just about exactly what we see there. So now for the excuses. Well, I know what Bev's going to say. He's going to say they were just taking a picture of the measuring rod and the tower happened to be in the background and mean old blue's not playing fair. Or he's going to tell us that the auto level has a maximum suggested working range, which is true if you're trying to read a measuring rod, but we're not trying to do that. What I'm doing is looking at where it's striking that building in the distance. Actually, what it boils down to is reasons. So what conclusions can we come to? Level clearly and measurably deviates from horizontal over distance, and it does so at a rate of 8 inches per mile squared. We've proven that. This effect can be confirmed both qualitatively and quantitatively. We've just shown you that. And Bev's assumption that level is horizontal is absolutely false. So I got one final question, Bev. You still think this was a good idea? Hey, thanks for watching.